Okay, so welcome everyone. I'm Marina Martínez, as Elena has said, and I'm going to present some of my work in this contest, which is titled Thermoelectric Materials Using Waste Heat to Produce Electricity. And this research has been carried out in the Inorganic Chemistry department in the Universidad Complutense de Madrid. So first of all, as we all know, we are in a climate crisis, but the thing is that it doesn't seem to be getting any better because for the last years, the energy demand has increased and the perspective is for it to keep increasing. And the main problem is that most of the energy supply comes from burning oil, natural gas, or coal. So at the end, if we just look at 2019, 81% of the energy that was supplied was coming from non-renewable sources. So we need more energy, and we are generating it just burning more fossil fuels, which only increase the amount of CO2 in the atmosphere and make the climate crisis worse. In this way, I think that thermoelectrics could be really interesting because they can convert heat into electricity. And this heat can come from waste heat in many contexts, in many different industries. And so now I'm going to explain a little bit more how a thermoelectric works. So it works with this kind of modules. It has a hot side and a cold side. And when we have this temperature difference, a current difference is produced between the two cables. What is happening inside? So as we can see, these two materials are a combination of two types of materials with different charge carriers. And that makes that when the temperature difference is implemented, the charge carriers migrate to the cold side. And so here, for example, a positive density is generated, and here a negative density is generated. So we have the difference, and it generates the voltage. So here I'm going to show you an example. Here we have the thermoelectric module, as I was explaining before. The top part is connected to this jar, and the bottom part is connected to this other jar, and the cables are connected with the rotor. So if we add cold water and hot water to the other one, let's see what happens, how this thermoelectric effect occurs. So as we can see, it is something real. It's not just me making it up. It works, and I just want to highlight that this is not speed up. So the rotor actually turns at this high speed. So which are some sources that we can think of where we can implement thermoelectrics? Well, combustion engines in cars could be a really nice option, because from the total of energy applied with the fuel, only 25% is effective. And there is a lot of losses that could be useful to implement the effective power, and therefore reduce the amount of fuel required. But it can also be implemented in industrial processes, like in these chimneys. They are quite hot inside because of the gases, and it's cold outside. So there is a temperature difference there as well. It's the same with also with the renewable, with solar panels or windmills. Like, they can also implement some thermoelectrics to enhance the efficiency. It can also work with body heat for sensors. And nowadays, the most common application for thermoelectrics, it's in space aircrafts. The first one was launched in 1977, and is expected to keep working till 225. This aircraft is farther from Pluto. So thanks to the thermoelectrics, it sends information back to the Earth. So this is quite interesting application. In this case, the heat is generated with isotope decay. So the radioactive isotope, when it decays, it generates heat. And because it's cold outside, we have the temperature difference that we need to power the thermoelectrics. So the commercial thermoelectrics nowadays are mainly bismuth telluride, lead telluride, and silicon germanium for low, medium, and high temperatures. But these materials have limited applications, and you will wonder why. Well, these elements are scarce and toxic. They are also expensive. Its efficiency is not really high. It's okay for some applications, like I said, with space aircrafts, but for others it's not. And they also react with oxygen, so they have a limited stability. So we need to find alternatives. So if we want to find alternatives, we need to know what is a good thermoelectric, and what defines how good is a thermoelectric is the figure of merit, which is calculated through this formula. On the top is the Seebeck coefficient, which is how much voltage is produced per temperature difference. We also have the thermal conductivity, how well does it conduce heat, and electrical resistivity, how well does our material conduce electricity, and also we have the temperature. So you will think that, okay, we maximize Seebeck coefficient, we minimize this two, and then we have the best figure of merit ever. But it's not that easy. These all properties are interconnected, so it's not that easy to maximize some of them and like to maximize all of them. So we have to find some kind of balance. And now I'd like to talk a bit more about the material we focus our research. It is marginite. It's a calcium aluminum oxide, and it's in cement, so it's a non-toxic material. It's really low cost. It's air stable because it is an oxide. And if we pay attention to the most abundant elements in earth crust, we see that out of the 5 more abundant, 3 of them compose marginite. So it's really a material compound with earth abundant elements, which is a really nice starting point. But let's get to know marginite a bit more. Marginite has a complex crystal structure, but I'd like to focus on these cavities. In these cavities, there is some oxygens that are more loosely bonded to the structure, and this oxygen can be substituted to electrons. So, and you will wonder why would I want to do that? Well, it's because when we do that, we go from an insulating material to a semiconducting material, and thermoelectric materials are semiconducting materials. So the possibility to change this is really important when thinking about marginite as thermoelectric. But yeah, so far I've described how marginite works, like some characteristic of it, but how is it as a thermoelectric? Well, if we consider again the formula, marginite has a high Seebeck coefficient, which is nice. It has a low thermal conductivity, which is also nice. And it has a high electrical resistivity, which honestly is not that nice. So we try to find some alternatives to improve that. And we come up with 2 ideas, like the reduction of marginite and the addition of conductive carbon. So the reduction, I mean the process I was explaining before, is just substituting this oxygen with electrons. As I said, that change from insulating to semiconducting. So it reduces the electrical resistivity. And how we do this reduction, we use the technique called spark plasma sintering that helps us to do that. And we also add some amounts of graphene to enhance also the electrical conductivity. So these are the materials that we obtain. All these 4 have been reduced with SPS, and these 2 have also carbon. And if we analyze the amount of oxygen, we see that we go from the original one with 33.5 oxygens to 32.6. So we actually achieved the reduction that we wanted. But how does it affect the electrical resistivity? Let's see about that. So we were in the first place in these orange triangles. When we apply SPS processes, we go to these 2 kind of samples, depending on the time we apply. So we reduce the electrical resistivity by a power of 1,000, 10,000, it depends on the temperature, but it is a great reduction of the electrical resistivity. But when we add graphene as well, we reduce this resistivity even more. We reduce from here to here, there's 1,000,000 times a reduction, because this is a logarithmic scale. So we actually achieve a great reduction of electrical resistivity. And let's see how it affects the thermal conductivity. So we, in this graph, we see that between all the samples that we have studied, there's not much difference. Like if we look at this scale, is not really large difference. So there's not, so while we really did reduce the electrical conductivity, which is also represented here in blue at a constant temperature, we kept the thermal conductivity almost constant. So we have the ability to uncouple the electrical resistivity and thermal conductivity, which is a great thing when we're talking about thermoelectrics, because as I said, all the properties are usually related. So uncoupling is really nice. So finally, I'd like to sum up all the ideas that I've been talking about. So thermoelectrics, climate crisis. Also, marginite is an appealing material because it's non-toxic, it's abundant, and it's low cost. And we here improve the electrical conductivity, and at the same time, we keep constant the thermal conductivity. So we uncouple the thermoelectric properties, and in this way, it is a nice path for novel thermoelectrics that are less toxic and more useful. So thank you so much for your attention, and please, if you have any questions, I'd like to answer them.